Hello everybody, I hope everyone is fine. Today there will be some question regarding the biasing and amplification. So this is a GATE 2019 question, okay, where you can see that there are 4 transistors where 3 of them are PMOS and 1 is the NMOS, where this NMOS is the amplifying device. And on the left part you are seeing that there are 2 PMOSs which are diode connected, because you can see that the drain is connected to the gate, okay, and in PMOS the source is always kept at a higher potential. So here the source of the upper PMOS at the left, the source is kept as a 4 voltage, which is a higher potential. In the question, mu n and mu p are the carrier mobility. One interesting fact I will tell you later on regarding this. And COX is the oxide capacitance, which is same for all the Mosfet over here. And then there is no channel length modulation or say body bias. Okay, and so we need to find out the gain of the circuit. So what is the ratio of V out by V in? And one point regarding body bias, I'm saying that the PMOS is always connected to the higher potential. Okay, so here the top left PMOS, no problem. Already your source and body are connected to the high potential. Even it is for the right up PMOS also it is same. Even for NMOS also the body is connected to the ground. But what about the left down PMOS? There is a finite body to source voltage, but here we are ignoring it. If you look at the circuit, in the left part there are 2 diode connected PMOS. So this diode connected PMOS are acting like a voltage divider. Okay, and if you see the voltage from source to gate of the upper PMOS, that is 2 volt, which will be act as a voltage to source volt for the next PMOS, which is given at the top right. So as per the question, you can see that the mu p COX for the PMOS is 30 microampere per volt square, and W by L of the PMOS is 10, and for the NMOS the mu n COX is equal to 60 microampere per voltage square, and the W by L of NMOS equal to 5. Generally what happens that the mobility of the electron is found to be much higher than the mobility of the holes. Okay, in silicon, if the mobility of the holes is around 400 or say 450, then the mobility of the electrons is around 1300. This is for a particular temperature, particular process and everything. Okay, I'm telling. And say in germanium it is almost doubled. And in gallium arsenide it is the mobility of electron is quite larger than the mobility of the holes. So here what they have assumed, what I can see, that if you see that the COX terms is common, so the mobility of electron here is twice than the mobility of the holes. So to get the same current flowing, what they did, first of all they assume that the say both are in same region of operation. Say we are since it's an amplifier, so we are considering that both of the transistors are in saturation. Let's go to the next step. Okay, so they are already in saturation, and say if you keep the overdrive voltage for both of the transistor, say for the upper PMOS and the bottom NMOS same, that you are keeping the overdrive voltage same and you are just ignoring the channel length modulation. So only thing is that only parameter which you have is controlled by your width. So because your length is same, your length for PMOS and NMOS are same. So only thing which you can which is in your control, that is width. So because of that, to have the same current, but since the mobility of the electron is almost twice over here than the mobility of holes, so the width of the PMOS is kept twice than the width of the NMOS. So this is a basically thumb rule which we generally take while we are designing. Let's first focus on the bias point, and then we can go to the AC analysis and all. But anyhow we need the AC analysis. Like in the question it is said that we need to find out the gain of the amplifier. But first let us see that what is a bias point. Okay, if you see the left part where there is 2 diode connected, then so it is a voltage divider. Okay, so your voltage from source to gate in both of the transistor, the voltage from source to gate is 2 volt. Okay, and even in the topper one I have already described that voltage from source to drain. Voltage from source to drain of the upper PMOS is 2 volt, and the source and drain are connected. And in the bottom one, from your source, the bottom PMOS from source to gate, or says from source to drain, it is 2 volt. Here in the bottom transistor the drain is connected to the lower potential, that is my ground. Okay, and if you see the AC analysis, it is basically a diode connected. You just set up your bias point, that's all. And your threshold voltage is also given. Okay, so now this is the exact picture which I want to say you, that there is 4 volt and then there is a 2 voltage source to gate. Okay, and this source voltage which is there in the PMOS is going to set up the current, the bias current which is going to flow through the PMOS and through the NMOS. And already it is already set in the bias, means already set in the saturation point, assume it. And the voltage also at the NMOS is set in such a way that this NMOS will be also in saturation. Okay, and this PMOS, how can you say that it is in saturation? If your say 4 volt minus V out is greater than your overdrive voltage, then it will be in saturation. As I told you earlier, that the current which will be flowing through the PMOS and the NMOS has to be equal. So if you just calculate, because you know mu P COX into W by L PMOS, we have the values, and we are just assuming that mu P are in saturation, and then you have that VSGP value also, and VTP value is also given. That will give the value as 150 microampere. Since 150 microampere current has to also flow through the NMOS, so from there we have the values like mu N, COS, WL, and MOS. So there your VGSN, if you just calculate, then your VGSN will come out as 2 volt. So it is already, so your overdrive will be 2 minus 1, that is 1 volt. And also we are ignoring the channel length modulation, but just saying that since both are in saturation, so you can just consider that the VSDP, the voltage from source to drain in the PMOS, and the voltage from drain to source in the NMOS are also same. So the two voltages, which is the voltage of drain to source, which is in the NMOS, and the voltage from source to drain, which is in the PMOS, if you sum of them will be equal to 4 volt. Okay, so each of the value which is the drain to source, that will be equal to 2 volt. So your both the transistors are in saturation. So my NMOS is in saturation and my PMOS is also in saturation. Okay, so in the NMOS, what we are doing, on the top of this VGSN voltage, we are applying a small signal, an AC signal, which is given as Vin. Okay, and this Vin is going to amplify, and then what we will get, then we will get this AV into Vin. I am talking here, this is a large signal analysis. Okay, and here is the small signal analysis where I have removed all the DC values. Okay, proceeding further, you can see that both the diode connected are in parallel. So basically it doesn't has any contribution. So in this equation, this upper PMOS is nothing but it has a resistance which is given as RDS. So it has an RDS P which is of 6 mega ohm, and for the NMOS, if you just go through the small signal analysis, then you will see that this NMOS, whatever there is a AC signal which is applied across the gate to source of the NMOS, and then current from drain to source will be created because of the applied gate to source voltage. So this AC signal is going to create current from drain to source, which is GM into VIN. Okay, and this GM value I don't know, which I shared as GMN. Okay, this value I don't know, and RDS is already given as 6 mega ohm for both the transistor. Okay, so my small signal equivalent circuit reduces to this one. So now what's left? We have to find out that what is the voltage gain. Okay, so I have already said you that the VN, the applied VN, is going to create a current from drain to source, which is my GMN into VN, and that the same current is going to flow through the parallel combination of RON parallel ROP. Okay, if you see this diagram, then you can notice that this ROP and RON are basically in parallel. So the current GM and VIN is flowing through the parallel combination of RON and ROP. Since RON and ROP, which is already given as RTS, so since both are equal, so when two equal resistors are in parallel, so the equivalent impedance or the resistance becomes half. As for a same equal voltage, if there are two paths, two equal resistive path, but since the voltage is equal across them, so naturally double current will flow, so the equivalent resistance is going to be half. So 6 mega ohm and 6 mega ohm are connected in parallel, so your effective resistance will be 3 mega ohm. Okay, because the double current will flow, right? Okay, this parallel combination is a must, is very much required in designing an amplifier. Okay, so instead of load, we use this PMOS as a load. Okay, this PMOS and NMOS combination, okay, it comes into picture. Okay, and if you see the current which is GMN into VGSN or GMN into VIN, that is flowing from drain to source. Okay, but when you are calculating V out, your V out is already as a drain, and you are calculating the potential from drain to source end. So naturally the current is flowing in the reverse direction. So what will be your V out? V out will be minus GMN into VIN into 3 mega ohm. Now we don't know about the GMN. So, but we have the VGS, even we have the current value which we have done. So let's talk one by one that how we calculate the GMN value. We have three formulas to find out the GM. You can apply any one of them, whichever you want comfortable. Okay, suppose you don't have the value of the overdrive voltage, then the first formula you should use. Suppose you don't have the value of mu n COX W by Ln, then you should use the second formula. And say if you don't have the value for the current, in this case current value is not given initially. Okay, so then you should use this formula, this third one. So mu n COX is already given, which is 60 microampere, and your W by L ratio is also given, and overdrive voltage that you have to find out. But unfortunately here, first what we have done, we got the value for that, what is the source to gate value of the PMOS, and from there we have calculated the drain current which is flowing, and from there actually we have got this overdrive voltage for the PMOS. Okay, so you can use the first equation where your drain current is 150 microampere, and if you just put the value, your GMN will be equal to 300 microampere per volt. Okay, and in the second equation you also have the VGSN minus VTN. So over there, if you just put the value there also, you will get 300 microampere per volt. We would not say much, because here out of these three methods, only this method came out to be fruitful, okay, and less time consuming. So if you know if you can calculate the drain current, then in one step you can get the value for the transconductance. So the value for GM is 300 microampere per volt, and my resistance, which is a parallel combination, that is 3 mega ohm. So now you just multiply it, so you will get minus 900. Listen, one thing, just see the circuit. This is a common source amplifier, so the voltage gain has to be 180 degree out of phase. So the value for the voltage gain, which is V out by VIN, has to be minus 900. Okay, I am ending over here. Before ending, I just want to say one thing, that say for an NMOS which has an impedance of RO, okay, output impedance which is from drain to source, okay, and this is not a physical impedance, okay, this is not a physical impedance, this doesn't exist, okay. And for PMOS, say this is R naught. This impedance is only due to channel length modulation. So if you connect a resistor at the source, always remember at the drain the resistance is always higher. So if you connected a resistance at the source end, then from the drain end you will see it a much larger resistor. Okay, and if the MOSFET is connected in a diode connected, then you will see that actually the impedance reduces to 1 by GM. It is no longer R0. Okay, please share your views and comments, and if you have any doubt, then please let us know. Okay, we would love to answer your doubts. Okay, thank you everyone.